Scientists use stream monitoring in real time along with surveys of channels to understand the behavior of a river system as it floods and inundates. Here we see an example hydrograph and inundation map from the USGS. The blue swaths in these maps, they're not real photos of river width and extent. Instead, they're modeled outputs of the inundation of the river at different stages and discharges. Maps like this are publicly available to every citizen so they can learn about hazards in their area and make better informed decisions. The colors you see in the hydrograph at left correspond to flood risk levels. I'll go to an example from the Boulder River flood in 2013 to better discuss these. This is the hydrograph from the Boulder River as recorded in the town of Boulder, Colorado. In the example hydrograph earlier, we plotted discharge versus time, but now on the left-hand side, the left y-axis, we see river height. Recall that river height and stage relate to discharge, which is on the right axis, but they don't have a linear relationship. And as stage goes up, increases in discharge that you see on the right are magnified, since a lot of the water that is flowing is inundating rather than rising. We're looking at the river level and discharge from September 7th to 12th of 2013. This is the blue line. Beyond the September 12th point that this was recorded, the purple line is a forecast for potentially what would happen next over the next day, and it's based on modeling. Record rain fell across the Colorado Front Range in September of 2013, dropping the equivalent of a year's worth of precipitation in just a few days. As the river rose during the storm, it entered several stage levels. These levels are defined by the degree to which they threaten structures and overtop banks. Firstly, at the action stage, the river water surface is near or slightly above the top of its banks. This is the stage where you want to take note, and generally no man-made structures are flooded, and any land that is limited to small areas of parkland and marshland. Then the stream rose to a flood stage. At the minor flood stage, minor flooding and inundation occurs, and typically at this stage some roads and parks are covered with water. Inundation of buildings usually begins at the moderate stage. Roads are likely to be closed and some areas cut off in this period, and some evacuations may be necessary. At the major flood level, the river flooding is significant to catastrophic and life-threatening. Often there's extensive flooding with some low-lying areas completely inundated and structures that may be completely submerged. This is the stage at which you might have a large-scale evacuation, and it's the one that the Boulder River basically stopped right at. Lastly is the record flood stage. This is the level at which the river is at its highest it's ever been since records began for the area where the stream gauge is located. This does not necessarily imply a major flood. Some areas have just never experienced major flooding, and thus a record stage is not that high. The chance of getting a major flood like this is rare, and some referred to this one in Boulder as the 100-year storm or the 1,000-year storm, and maybe a 100-year flood, referring to the amount of rainfall and the amount of flooding. The greater the magnitude an event, the less likely and often it is to occur, and we can see this relationship here. At the top of the graph, we have a low magnitude river flow, what we might call an annual flow that occurs with a high frequency every year. At the other end, down to the right, we have a higher magnitude flood. This is less likely to occur, and these relationships for rivers are generally derived from real data, which sometimes might be quite limited. When someone calls a flood a 100-year event, it just means that it's calculated to have a 1% probability of being exceeded in a year. A 50-year flood has a 2% chance of occurring, and a 10-year flood has a 10% chance of occurring. These floods could occur back to back in 2 years. To better understand these terms and how they're determined, follow the link and watch the video. Combining monitoring through stream gauging with history and mapping and modeling allows us to be able to understand river behavior over space and time, not just at a single reach or monitoring station. It's critical that this knowledge be communicated to the public, land managers, and public officials so they can understand risk and make informed decisions. And this is done most clearly by flood hazard maps, such as you see here. The channel here is a regulated floodway, and the colors correspond to flood risk and probability. The blue swath around the rivers represents the area with a 1% annual chance of flooding. And the orange swath outside it has a 0.2% chance. These colors don't actually represent the natural flood paths and extent of this stream. And in this area, the Tennessee River around Chattanooga has been controlled. It's regulated because of the infrastructures and communities that have developed along it. The river in this section actually bends down and back up to the left. And look at the extent of potential flooding and inundation there. Publicly available flood maps are federally required and available at a lot of different levels. Some counties and states have their own online map viewers that are easier to use and navigate to learn about flood risk in their region. I've provided a link to a viewer from the Federal Emergency Management Authority, FEMA, who oversees the federal regulations for flood insurance and flood mapping. Follow the tinyURL link to get a close look and to see information about your local area and streams. You'll need to zoom in really close, change your layers, and turn some on and some off to get the view I showed in the prior slide. Of note here, some local municipalities and counties may and likely will have better and more updated versions, potentially that are easier to navigate than this one. Rivers pose risks and rewards, and systems such as this have fertile soils, abundant water, and means of transportation. This is why we develop around them. But rivers are also dynamic, not just because they flood, but because they're constantly moving and changing, even in what might be considered flat plains such as this. The change we see in this river over just 20 years is more dramatic than many, but it does highlight how a system that we might view as static when we're standing on its banks doesn't really care where you build houses, put farms, or construct entire cities.